Right. Here we were. So we were discussing the standard oxidation potentials, right? Chemical properties with air, they form oxides, and with nitrogen in the air, they form nitrides also. But this point you remember, beryllium and magnesium are kinetically inert. They do not react with oxygen and water directly because an oxide layer is formed on their surface. See, beryllium is behaving like aluminium. Aluminium may be you see na ki there is an oxide layer. Same thing is observed here also. Okay, but once you powder them, then yes, they react brilliantly. They burns brilliantly on ignition in air to form oxide and nitride, BeO3N2, MgO and Mg3N2. This is blue Melicky line is very important. Magnesium burns with dazzling brilliance. That is very beautifully it burns in air, okay, and releasing light, forming MgO and Mg3N2 both. Calcium, strontium, and barium, if you talk, then they are attacked readily by air, forming oxide and nitride. Okay? Let us go to reaction with water. If we talk of reaction with water, again, beryllium and magnesium, due to small size and oxide layer formation, will be very slow to react. But others, as you go down the group, they will react faster. Okay? Liberating hydrogen gas. Particularly if I talk of beryllium, beryllium do not react like this so easily. It reacts only with steam. It do not react with water, it reacts with steam. Magnesium react with hot or boiling water. Rest all react simply with cold water also. If you talk of reaction with acid and base, only and only beryllium will react with base to form berylate, BeOH4 to negative an ion. Otherwise, all of them will react only with acids because only beryllium is amphoteric. Others do not. Okay? Others are not amphoteric. Take reaction with hydrogen, they form hydrides of the formula BH2, except beryllium again, because it will form some polymeric form of hydride in a very different way. It won't react directly with hydrogen like this. Take beryllium and magnesium hydrides are covalent, whereas rest all are ionic. Take BH2 is prepared by reaction of BCl2 with LiLH4. You cannot prepare directly BeH2 by this beryllium and hydrogen reaction. You have to prepare indirectly. Okay? Remember this. BH2 is prepared by reaction of BCl2 with LiLH4. As I have already told, BH2 exists in polymeric form. Okay? Like this. And similar will be the tendency of BeCl2 also. Similar behavior, though the bonding will be slightly named differently. Here I am saying it is 3-center 2-electron bond. Okay, 2 electron, 3-center. This type of bond is formed and ultimately giving it a like this tetrahedral appearance for each beryllium. One BH bridge like this, one in perpendicular, type this, it goes. MgH2 also form polymeric and is covalent. Hydrides of all other are ionic and behave like first group saline hydrides. Okay? If you talk of reaction with halogens, they can react directly with halogen or can react with HX acids. Okay? BF2 is prepared by thermal decomposition of NH4 to BEF4. Otherwise, it cannot be prepared by this method. Beryllium fluoride is not prepared by this method. And BCl2 is prepared entirely different method. BO plus carbon plus chlorine. Okay, you have to take carbon also, which removes oxygen, carbon monoxide. Very important reaction, BO plus carbon plus chlorine. Now, BCl2 pe you have lot of questions asked. Take BCl2, BF2, these are all covalent, whereas other are ionic halides and their ionic character will increase down the group. BeCl2 in solid state exists as a polymer like BeH2. But the bonding is different, as I have already told. See, chlorine, okay, like this. Again, same, perpendicular. But I'm not saying it is a 2 electron 3 center bond, because here you will have a coordinate bond from one chlorine to beryllium. Okay, like this. So I cannot call it 2 electron 3 center bond. Okay, here chlorine is forming a bridge bond like this, bridging kar rahe. In gaseous state, it exists as a dimer like this. Only two BeCl2 will combine. In solid state, it is polymer. In gaseous, it is dimer. If you heat it beyond 1200 degrees centigrade, then you can have the monomer also. Okay, beyond 200 degree, you can have monomer also. Otherwise, it is only till dimer in gaseous state. Important compounds of second group: oxide, peroxide, and superoxide. Beryllium and magnesium will form only oxide. Small size, that is why. Take of the formula BeO for beryllium, MgO for magnesium. Take BeO is covalent, rest all are ionic. They are basic in nature and their basic nature increases down the group except beryllium, which is amphoteric. We have already discussed it so many times that beryllium will behave amphoteric, forming berylate. BeOH42 minus is what you need to remember. No one in the group forms superoxide. Superoxide was characteristic of first group. From potassium, rubidium, and cesium, we expected superoxides. But in second group, you have only oxide and then peroxide. Calcium, strontium, and barium can form peroxide. Take increasing ease and stability of peroxide is observed with increase in metal ion size. Importance of this peroxide: BaO2 plus twice HCl. This is one of the method of preparation of H2O2 we have done in hydrogen. MgO, it is called magnesia and is obtained by heating natural magnesite. What is magnesite? MgCO3. This MgO is important because it is used in manufacturing refractory bricks for furnaces. What are refractory bricks? The bricks used inside the furnace, which can survive very, very high temperatures. Okay? It is slightly soluble in water, imparting alkaline solutions. Next is CO as oxide, which is important, called quicklime or lime, prepared by heating CaCO3 at 1000 degree centigrade. Okay? It is white amorphous powder. It emits intense light when heated in oxygen hydrogen flame. Certainly, it is a basic oxide, so it reacts with acidic oxide, and therefore it is used for slag formation in metallurgy. Right? It is used for slag formation in metallurgy. It combines with water to form slaked lime. Of course, slaked lime is the suspension of calcium hydroxide, and clear solution is called lime water. Okay? Nitride. Magnesium form nitride, though all form nitride of the formula M3N2, but the magnesium is more important, which on water or hydrolysis release ammonia. All of them will release ammonia. See, hydrides, they form ionic hydrides with the formula MH2 except beryllium, as I have already told, because it is a polymeric hydride. Hydroxides of the formula MOH2, all of them form such hydroxide. Right? We have already discussed how they will form. Beryllium will react with steam, magnesium with hot water, others with cold water. Now, important hydroxides. Magnesium hydroxide is called milk of magnesia. It is used as antacid under the name gelusil. See? It dissolves in NH4Cl. See, like this. Acid-base reaction is happening and it is dissolving like this. Thus, MgOH twice is not precipitated from the solution having Mg2 plus ions by NH4OH and excess NH4Cl. This is what we are talking of qualitative analysis, third group reagent. There it won't get precipitated like this. MgH twice is a pink color suspension when used in antacid. Okay, that color के तौर से use करते हैं, antacid के तौर से use करते हैं. Calcium hydroxide is called lime water. Suspension is milk of lime. It is sparingly soluble in water. Its solubility in hot water is less than in that of cold water, right? Because its solubility is exothermic, that is why. Hence, its solubility decreases with increase in temperature. It readily absorbs CO2. Yes, that is why it is used in test of CO2. It is used in mortar. Now, what is mortar? When we set bricks, then between the two bricks, you put some paste, na? That paste is called mortar. So what is mortar? Mortar is a mixture of one part of slaked lime and a calcium hydroxide suspension, 3 parts of sand, SiO2, rake, plus water, and then paste is made. That is called mortar. In that, we are using calcium hydroxide. Barium hydroxide is called barita water. We have already discussed solubility of second group hydroxide increases down the group. Halides. Same, second group BeCl2 done, MgCl2 I have already told you. And it exists always as hydrated form. If you want to dehydrate it by heating, you will not get anhydrous MgCl2, you will get MgO. Okay, such a strong affinity towards water or oxygen, but not to chlorine. Sorrel cement, it is a mixture of MgO, MgCl2 paste is prepared, which is set to hard mass on standing, and it is used in dental filling, flooring, etc. Very commonly used in dental filling. If you'll go to dentist to get a filling, this is what they will use. They will immediately take a small cup or something, take this sorrel cement, add water, and immediately they will fill. Okay, they won't let it be left in the atmosphere for some time, otherwise it sets and become hard. Okay? CaCl2, it is a byproduct of solvay. What is its function? Nothing new. We have already done it, that it is used for dehydrating or drying gases except for ammonia and ethanol. Moving to carbonates. If we talk of carbonates, yes, in second group, MCO3 and MHCO3 whole twice, these are the formula. Thermal stability will increase with increase in size of cation, and water solubility will decrease because the usual tendency down the group, water solubility will decrease. Why thermal stability is increasing? Because if the cation is of small size, it will have strong polarizing power. Okay, it will attract this negative cloud of oxygen and break this to oxide and CO2. So small cations have high polarizing power. So low thermal stability. BeCO3 stabilize or rather decompose but below 100 degrees centigrade. Magnesium carbonate 540, calcium carbonate 900, strontium 1290, barium carbonate C 1360 degrees centigrade, it will decompose. Bicarbonates of second group are found only in solution. You will not find their solid bicarbonates. Okay? Particular about CaCO3. CaCO3 in nature is found in so many enormous forms. Marble, limestone, chalk, coral, calcite, etc. Now you are aware of the thing, something called polymorphism. See, CaCO3 has two polymorphs, calcite and aragonite. See the calcite, the transparent crystal type appearance. See aragonite. See, these are the actual appearances, but of course the color in them is due to impurity. I'm just showing, see the transparency and see the different appearance, different polymorphism. When observed in elements, then you call it allotropy. When you observe it in compounds, then we specifically continue to use the word polymorphism. So the two polymorphs of CaCO3 are calcite and aragonite. ठीक? Out of the two, remember calcite is more stable. This orangish one is more stable. Clear? ठीक? Rest all we have done. Sulfates. Second group sulfates are stable, but on heating they decompose, giving SO3. Same way their stability goes increasing down the group. Like carbonate, nothing new. Important is gypsum. CaSO4 dot 2H2O, if heated to 150 degrees centigrade, it forms plaster of Paris. Around 200, it forms dead burnt. If further heated, then it forms CONSO3. Similarly, you must be aware of something called MgSO4.2H2O, right? Ipsum, 7H2. So Ipsum these days is very commonly used salt for what should I say? हिंदी में तो उसे सेकना बोलते हैं, लाइक क्या बोलते हैं, वार्म करके यू कीप योर लेग्स, यू वार्म दिस सॉल्ट or you warm water, add this salt and put your legs in it to have the relief in swelling and this. So what you call warm water may you dip and have the relief of. So English में I don't know what to call. In Hindi we can say सेकना. ठीक. So moving further, nitrates, same. Second group nitrates are unstable. They decompose to oxide, NO2 and O2. Carbide. Group 2 metals. See, first group didn't form carbide. They form ethanides. But second group form carbides. They form ionic carbide of the formula MC2 except beryllium. Calcium, if you are heating with carbon, you are having CaC2. ठीक? Same way. If you heat CO with carbon, you will have again CaC2. Acetylide is there. ठीक? This compound was used as a source of acetylene for oxyacetylene welding. This page is important. If you heat this CaC2 with nitrogen at around 1100 degrees centigrade, calcium cyanamide called nitrolim fertilizer. Remember, this nitrolim fertilizer is not just calcium cyanamide, it is both. Fertilizer is both. Okay, is formed. Now, this fertilizer, when added water, finally gives urea. You add it to plants and you add water, then ultimately its functioning part is urea only. But it also has other important industrial use. This calcium cyanamide CaNCN has commercial use because it reacts in different ways, forming different compounds. But very important, it forms something called melamine. I hope you all must have gone through the polymer chapter and memorized number of lone pairs in melamine, number of NH2 groups in melamine. All these things are the numerical which are frequently asked. Okay, but this is only tendency of calcium. BaC2, if you heat it with nitrogen, you will not get BaNCN. You get normal barium cyanide. Only with calcium, you get CaNCN, and from which this entire thing ended up to melamine. Okay? If you have Be2C is formed, if you want to form Be2C, then you have to heat beryllium oxide with carbon. See the temperature, 1900 degrees centigrade, and you will get Be2C, which will give methane and hydrolysis. Magnesium, MgC2 on heating changes to Mg2CH3, which is giving you propine on hydrolysis. Other thing is complexes. Both group and 2 form complexes, but relative stability of second group complexes is more. Chlorophyll, the green color of plants and algae, that is due to chlorophyll. In that, see, magnesium is there in the center. So it is a complex having magnesium. Very important complex from second group. Then see, this is beryllium acetate. See, calcium EDTA complex. So these are all famous complexes of second group. Anomalous behavior of beryllium, if I talk, again, same thing, charge density, charge upon 4 by 3 pi r cube. Due to that, it shows different behavior as compared to other members. And due to exceptionally small size. Beryllium does not exhibit coordination number more than 4 as its valency shell are only 4. Okay? Others can exhibit 6 or more by using their d orbital. The oxide and hydroxide of beryllium, unlike hydroxide of other, is amphoteric. If you talk of diagonal relationship between beryllium and magnesium, again the same, the similar charge radius ratio. Charge density, they are again talking. Like aluminum, beryllium is not readily attacked by acids. Take beryllium hydroxide, like aluminum hydroxide, is amphoteric. Chlorides of both beryllium and aluminum form bridged chloride structure in vapor phase. Both the chlorides are soluble in organic solvents and are strong Lewis acids. They are used as Friedel-Crafts catalyst. Beryllium and aluminum ions have strong tendency to form complexes. Use of secondary groups. Please make a small list type thing of this. Okay, like point wise, if you can make that copper beryllium alloys, where are they used? Like this, as where metallic beryllium is used in window. This is so important, very important. This metallic beryllium is used for making windows of X-ray tubes. Okay, very important. Magnesium alloy, aluminum alloy is used in aircraft construction due to its light mass. Okay, these are all important points. You have to remember them. If you go down here, calcium and barium metals owing to their reactivity with oxygen, ठीक, and nitrogen at elevated temperature have often been used to remove air from vacuum tubes. Radium is used in radiotherapy, for example, in treatment of cancer. ठीक? Biological importance, again important. See, the calcium concentration in plasma is maintained by two hormones. You have to remember calcitonin and parathyroid. These two hormones control it. Take magnesium is used in our body along with ATP, adenosine triphosphate. As a cofactor, it is there in chlorophyll. Take 99% of body calcium is present in bones and teeth. It is also important neuromuscular function. Somewhere here it is also very important line return that the bones and the teeth. Do you know that bone is not an inert and unchanging substance, but is continuously being solubilized and redeposited. That is why we need a continuous supply of calcium. If you do not eat calcium on regular basis, you will suffer a disease called osteoporosis. Okay, there comes cement. I will say cement. Please read this cement notes, this component. Okay, cement is basically CaO, rich in lime, is a product obtained by combining a material rich in lime. Okay, इसके अलावा besides lime, it will have SiO2, it will have Al2O3, it will have Fe2O3, okay, MgO, different cement materials are there, but the major component is always CO, 50 to 60%. Second major is SiO2, and then comes Al2O3 and Fe2O3, other components. See here, this line. For a good quality cement, the ratio of silica to alumina should be between 2.5 and 4, and ratio of lime to total of the oxides, SiO2, aluminum, and Fe2O3 should be close to 2. This is important. Okay, this line you have to remember. Clear? Uses, you all know cement uses. Setting of cement is an exothermic process. Okay? That brings us to the end of the theory of second group. Now, I have added questions in these slides in the end which appeared. Okay. Please go through them when you revise notes. Do you want to do them now? They are quite many. So either you do it, I'll share the slide with management and you can do these questions at your own revision pace. Okay? Is that okay, everyone? Say yes or no. Or you want to do now, then I can make it do, but it will get you a little late, as you wish. Okay, no answer. Fine. So I'll share the slide and you can do. Fine.